so let's first give you a short introduction about functional data analysis, kind of a general picture about functional data analysis. Okay, sorry, let me adjust my view. Okay, so so I have one question, like, so when I put my camera here, can you see, is that block your screen or it doesn't block your screen? So in my screen, I see, you know.
Yeah, we don't see that image here.
Oh, we don't see that. So you now you have my slides in your screen only.
Yeah, I can see the full slide. Yeah.
Okay, that's great. Okay, thank you for letting me know. Do adjustment. I think maybe I don't need to. Okay, that's better. Okay, let me give you an introduction about functional data analysis. So let's first learn about what is functional data. And so I'll give you some examples about functional data, some typical examples we will see when we do functional data analysis. So the first example is the data showing on the left. So they are the electricity usage every month in 78 cities. And so here, the electricity usage for each city will be one curve. So now in the graph here, we have 78 curves. And so you can see here for this data set, we call it functional data because the electricity usage can be treated as a function of the month or the function of the time. So, and also when we see the electricity usage, we will assume that, you know, the use of the electricity usage will be changed continuously or smoothly. This is a very important feature for functional data analysis. So here, our goal here is try to explore the major source of variations among 78 curves. Okay, so this is the first typical functional data. So this is the second example about the functional data. So basically here, we record the position of the pen when we write FDA, the 3 letters. And so we write these FDA letters for 20 times. And so we recorded the position of the pen on the paper. Okay, so here, basically we have the X coordinator and the Y coordinator of the pen position. Okay, so if we write this the X coordinator and the Y coordinator as the function of the time, then we will have this 20 paired curves on the top and bottom graph. So again, here, these data are functional data because the position of the pen can be treated as a function of time. So so here, this is kind of give you ideas like the kind of characters for functional data. So first, functional data is often complex. So you can see here these curves kind of going up and down. It has a very complex trend. So also here, when we have these 20 curves, we can view as each curve as a single observations about the underlying process. Okay, so when we do the statistics, we often assume that the data coming RID, right, are coming from it is a identical independent distributed coming from the same distribution, right? So here, when we see the functional data, we view that each curve coming from the same stochastic process. Okay, so this is the functional data. And so here for functional data, you can see that main feature is that for this example, handwriting example, the measurements for each curve are pretty frequent. Okay, so this is kind of how functional data start. Okay, so when we think about the function, we typically want the function to be continuous, and we want to have many very dense observations for the function. Okay, so this is how functional data start, but I will show you later that actually with the development of functional data, we now can handle very sparse functional data as well. So I will show you later. And also, all these functions will have a similar trend. Okay, so for this example, you can see the trend of these four curves are pretty close. And the most important feature for functional data is that we assume that all this curve is a smooth function of the time. Okay, when we smooth function, I mean the derivative of the function is also continuous. So basically, functional data analysis means analysis of functions. Okay, so so these functions can be one-dimensional functions, like I show you this example is function of time. It can also be function of spatial locations, and in that case, maybe it will be image data. So image can be looked at as a function of two-dimensional spatial location or three-dimensional spatial locations. In that case, it will be can also be viewed as the functional data as well. So as I mentioned that all the functional data we view that functional data are repeated measurements of the same stochastic process. And because the functional data have a complicated trend, then it is not easily described by mathematical formula. So for example, if I give you these functions, it will be hard to write down the parametric forms for these functions. So this is another feature for functional data. So we typically will not make parametric assumption on the function. And also the variations between replications is hard to describe. So here are the summary for the characteristics of functional data analysis. So basically, the functional data are measure of smooth process over time, or some other spatial locations, or some other continuum. And also, we don't make any parametric assumption on this process. We will have multiple measurements on the same process, repeat measurements. And so we are interested to describing the variations of the process. Generally, the functional data are collected in high resolution with low noise. But I will see that this is not a requirement now. The functional data can be sparse. So it can be applied to any estimate of a smooth process. So in the general definition for functional data analysis, it will not only work on the functional data. So even the data is not functional data, but in the model, we may have a function, a parameter as a function of time. In that case, we will also view as a general functional data analysis, like the very coefficient model. FDA is relatively new, although now it has been like 30 years now. So still there are many open problems in this area. So now it's a very hot area in statistics, and so now if you open the almost or any issues in the journals, you will see several FDA papers. Okay, at the same time, functional data is pretty complex because the trend is complex, and we cannot make a parametric assumption on the curve functions. So and also the data typically will require pre-processing. First, we have to transform the data from discrete data to a continuous function. And the parametric inference is rarely available for functional data. So here, this is how this short course will offer. So basically, I will talk about some applications and basic methodologies for functional data. And I want you to, after this short course, I want you to know what can functional data do, and how we can do it. And so I will run all the FDA code in R. Okay, so there's also MATLAB package for functional data analysis. And so here I want you to, after this short course, I want you to understand and interpret the FDA results. So you will learn that actually not easy to interpret FDA results because we don't have any parametric assumption on the function. So we have to put a lot of efforts to interpret the FDA results. So I will show you the FDA package to analyze functional data, and so I will also show you some recent methods in functional data analysis. So I will not cover a series for functional data analysis, like the asymptotic distributions, reproducing kernel Hilbert space. So for this short course, it has a very minimum requirements. So as long as you know multiple linear regression, you should be able to understand what I talk about. yeah, so another beauty for functional data analysis is that it's very easy to start the research. So you will see that it has very close connection with multiple linear regression. And so for this course, it will be easier for you to understand the materials if you know R and if you know some basic matrix algebra, multivariate statistics. So here are the, so in this short course, I will mainly follow the book Functional Data Analysis by Ramsey and Silman in 2005. This is a very classic FDA book. And so if you don't have any idea about FDA, I recommend you to read this book. It's very easy to understand. I will see it's not like the typical statistical textbook. It had a lot of examples. And so another book I highly recommend is the recent book by Ramsey, Hooker, and Greaves, published in 2009. Is a functional data analysis with R and MATLAB. And so this is a smaller book and a shorter book. So nice thing about this book is that it provides the R and MATLAB code for all the examples and graphs in this book. So it's if you want to learn some details about R code, I recommend you to read this book. Okay, another book is also the book by Ramsey and Silman in 2002. Is called Applied Functional Data Analysis. Yes, I'm not sure how many of you have heard about this book. This book is less well known than popular than these two books, but this book actually I find it very useful. So in this book, it gives around 10 case studies about functional data analysis. So it's very enjoyable to read. You know, when they work on each application, each case, it's very easy to follow. Okay, so some online resources. So basically, I teach this FDA course as a graduate courses in 2019 at SF Stanford University as a 12 weeks 12 weeks courses. So in that course, I'm able to cover all the details in functional data analysis and also go through all the code very carefully. So if you want to get all the details, you can go to that page and download the slides, computing code. And also I post my lectures at a YouTube channel. So you can also watch the YouTube channel. And so for all the R code I show you today is using the FDR package. It is developed by Jim Ramsey. So there's also many FD package developed now in R. So this website is show you all the package in FDA. And so here also list so if you're not familiar R, so this website is providing you how to download the R and some basics about the R computing. So now let's back to functional data. So let's give you some more examples about functional data. And so here, so before we show the handwriting for the FDA 3 letters. And so we just mentioned that this is very dense, accurate measurements for the functions. But in reality, the data may be measured more noisily. So here, this is to show you the daily temperature and daily precipitations in Vancouver. So you can see here, the temperature measurements looks is pretty accurate, but for the amount of precipitations, it is more noisy, right? Okay, so this is one example for FDA. So although the data are noisy, we want to find a smooth process underlying this data. The second examples is about the growth data. So this is the height of I think it is around 20 girls from their year 1 to year 18. So about their height. You can see for this data set, the measurement is pretty accurate. We know it's very easy to measure the height. But at the same time, these measurements are not equally spaced. So you can see here, we have quarterly measurement. We measure the height every quarter in year 1, and after year 1 from year 2, we only have one measurement for every year until year 8, and after year 8 to year 18, we will have measurement every half years. So this is the we call it unequally measurements. I want to show this example specifically because this is a very good example to show the difference to time series analysis. So for typical time series analysis, they assume the data are equally spaced. Okay, so you can see here for functional data, the observations don't have to be equally spaced. Okay, because we treated the function as the curve as a function of time. So typically the first step we do is that we will transform the discrete measurements over time to be a continuous function. So therefore, so for functional data, the data don't have to be equally spaced. So that's so after transform to the continuous functions, we can do a lot of modeling and inference, and so we don't need to worry about the non-equally spaced data anymore. Another unique features for the growth data is that the height of the data are always strictly increasing, right? So in other words, all these underlying functions have to be an increasing function, and so this is constraints on the estimation on the function. Okay, so another examples is about the body fat percentage of body fat for 162 girls. How they change over time, and you can see that for this data set, it's much more sparse, and so on average, there's only 6.4 measurements for each curve. Okay, so we call it the sparse functional data, and so the measurement is also irregular. So you can see here the time to measure the percentage of body fat is different for different girls. Okay, so we call it irregular measurement. So the goal here is that we have this like sparse measurement on the functions. So we want to estimate the underlying functions. At the same time, we may also want to estimate the derivative of the functions. Okay, so this is another unique feature for functional data analysis. So because we treat the function is a continuous function, so we can actually look at the derivative of the function. So here, and I show you on the bottom line, its bottom panels is to show you 4 girls. And so you can see here, their measurements are pretty sparse. So for example, for this girl, it doesn't have measurements in the early stage and the later stage. But we can still able to recover the function pretty well. At the same time, we can also estimate the derivative of the functions. So this is another, interesting things about FDA. So for functional data analysis, it also have made some assumption. The most common assumption is that we assume the function data are coming a smooth process. Okay, so we want to assume that the function is smooth. So in some cases, like when we have the discrete data, for example, if we have data coming from a Poisson process, the data may be not as smooth, but we can view that the process is coming from its discrete process, but the underlying function is a smooth function. So that's another way to deal with the smooth of the process. And also the function are typically not easily parameterized. We cannot write down a formula for the function, and we will not make any parametric assumption on the function. We also have assumed that we have enough data to find the feature of the process, like the peaks. So if we don't have data about the peaks, show the peaks, then it's hard to identify the peaks. And we assume that the function has multiple measurements. We have repeated measurements. So the data don't have to be equally spaced or have a perfect measurement. So some common sources for the functional data. So it can coming from the medical monitoring, like the EEG data, or the medical image data, like the fMRI data. It can also come from biology, like the population of the animals, right? So it's also can be viewed as a functional data. Environment science is also have a rich area for functional data, like the weather data, pollution data, traffic data. They all can be viewed as functional time. And the psychology, when they have the measurements over time, multiple time, it can also be functional data. In economics, when we have the interest rate change over time, it can also be functional data. And so in the web data, when we have the eBay auction prices change over time, we have Google Trends change over time. they all can be viewed as a function web data, functional data. So here are some essential questions FDA tried to answer. Okay, so the first is how can we go from discrete data to functional data? Okay, so this one is more viewed as non-parametric regression methods. Okay, so because of the limit of time, I will not cover this topic, but in my YouTube channel, I have several lectures talk about how do we go from discrete measurements to functional data. So the second question is how can we describe the random variations in functional data? So this will be a method called functional principal component analysis. So we will start this topic after the break. Okay, and so next we want to see how can we do classifications for functional data, how we do the clustering for functional data, and how can we relate the functional data to other data, like kind of a linear regression model. We also have a linear regression model for functional data as well. And so some special thing about functional data is sometimes we may want to align the functions so that such that they have their peaks happening at the same time. And so this is called a registration in functional data. So we will not cover in this course. So another thing is that here in functional data, we treat each function as a smooth function of time. So therefore, we can look at the derivative of the function. So so we can study. We know the derivative measure the rate of change of the process. So we can study the rate of change of the process. Often in many applications, when you look at the functions, they are very similar. It's hard to see their differences. But if you look at their derivative, actually their derivative will show more variations. So this is an advantage when we look at the derivative of the functions. So we have two students working in time series analysis. So here, I listed the difference between time series analysis and functional data analysis because the data, both they are working on the data measured over multiple time. So what are their differences? Okay, so so the most, as I said, for time series analysis, their model typically assume that the data are equally spaced observed. Okay, so here is one assumption, like for classic AR1 model. You see here, they will have xt related to xt minus 1. Okay, so when they write the model, they actually write down the x as an index of t directly. Okay, so you can imagine that if we have missing data, not equally spaced data, then we will have some difficulties to work on these time series models. And a second special thing about time series analysis is that they typically assume the time series is a constant mean. They call it a stationary time series. Okay, but in functional data, we actually assume the mean to be arbitrary functions. Okay, and so in time series, they mainly focus on the estimate about the correlation between the data observed at this neighbor time, like a correlation between xt and xt minus 1. Okay, so they want to predict xt based on the history xt minus 1. Okay, so these are the main focus for time series. Okay, but in functional data, we will look at how the one function yt related to other functions xt. Okay, it's like a linear regression model. Okay, so we want to predict yt based on other variables xt. Okay, so this is the difference to time series. So as I said, the time series is hard to deal with missing data, but functional data actually is pretty easy to deal with missing data. Okay. Next, I want to look at the differences between longitudinal data analysis and functional data analysis. So we have one student working on longitudinal data analysis, and they are all both working on longitudinal data, right? The data measured over multiple time. So what are their differences? So in the past, we will treat that the longitudinal data analysis will more working on the kind of the sparse data, like when the longitudinal data is only measured over multiple time point, right? And so you can see now functional data typically will be working on more dense time series. But you can see now functional data actually can also work on sparse data as well. Like in terms of the models, so here I list a typical model in longitudinal data. So this is longitudinal data. Suppose we have variable yij, I the index for the subject, j the index for the time. So you can see here, we can write down yij as a quadratic function of time, okay? And we have the coefficient beta I0, beta I1, beta I2. Sorry, this should be beta I2. And you can see here, so we will look at the between subject variations, and we will assume that the coefficient beta I follows normal distribution with mean beta and variance sigma. So this part should be sigma. So here we treated the beta as the fixed effect or the population effect, and the beta I has the random effects there. Okay, so you can see here the major difference for longitudinal data analysis is that they typically have a parametric assumption on the function yit. So you can see here yij, they assume that is a quadratic function of time, right? Yeah, and so again, for longitudinal data analysis, they are hard to deal with missing data. So by functional data, we are easy to work on that. So for functional data, for each function yit, we will make any parametric assumption on the data, and so we will typically write down yit as a linear combination of the basic functions. So phi j t here is the basic functions. So it can be the B-spline basic functions or Fourier basic functions. We will explain that later. It can also be some basic functions estimated from the data. We call it empirical basic functions. So when we do the functional principal component analysis, we will come with the functional principal component. It can be treated as functions. So Cij here is the function of basic functions, coefficient of basic functions. For this short course, we will mainly focus on two areas. One is a functional principal component analysis. The second is the functional linear models. These are the, I will see the two most important areas or tools in functional data analysis. So we will cover these two topics in details, and I will show the R code as well. Okay, so this is kind of give you a short introduction about functional data analysis. Let's see any questions.